Welcome to the fourth seminar of the quarter. Today's speaker is Çetinkaya-Rundel, who is a professor of practice in the Department of Statistics at Duke University. We mostly know her because of her contribution to the Open Intro project, which resulted in several textbooks that we use a lot in our intro classes. Her work focuses on integrating reproducible computing, open source tool, and real-world data into statistics curriculum, which is what comes across from her textbooks too, and also her publications. And today's talk is titled "The Future of Statistics Education: A Computational Perspective," and I'm really excited to hand it over to her. Thank you.
Thank you. Thank you so much, and thank you for having me. It's wonderful to hear that from folks using Open Intro, because that was a PhD friend's project that started one late evening in my friend's office, and we thought we could maybe make free introductory textbooks. And then we went and presented at JSM, and I remember many senior faculty telling us, "You'll give up on this in 2 years. This is not going anywhere." And look, we're still alive. But today I want to talk about the future of statistics education, perhaps a computational perspective, but I'll be a little bit annoying. I don't do this to my students, but when I'm giving a talk, I feel like I can give a pop quiz. Why not? So here we go. We have a pop quiz. You've been given a data set. It's called Poisson.csv of count observations along with two features, numerical and a categorical one. And you're asked to fit a Poisson regression model to these data with R, report the estimates for the regression coefficients you obtain, and interpret them in context of the data. Now, if this was a homework question, what would my students do? This is exactly what they would do. They would just put it in there and upload the data set and, hit the ground running. And this is what it says as a result. Like, I went through the thing with ChatGPT. I actually created a new account so that it's like this fresh interface, no background information about me. I love that it says, would you like a complete report style answer? It kept wanting to help me with my exam. Like, it kept saying exam over and over. Then I went to Perplexity just to try something else, did the same thing. I'm not going to make you watch the whole 2-minute video of this, but one thing I want to say is I went through the thing and it says, okay, would you like to do something else, like a follow-up? And I say, that sounds cool. Let's go ahead and do that. And then I go get taken elsewhere to Perplexity Computer. And guess what? It says, do you have a credit card, basically? And then we come back to the free zone. And then I ask for some model diagnostics. And you can see here, free preview limit reach. So I mentioned by happenstance that I believe in open source education and I believe in delivering information for free to people. I also believe in integrating new tools into our toolkit, and AI is certainly one of them. But this constant "I want your credit card" thing is really rubbing me the wrong way, I can tell you. I also went and asked Claude as well, because that's the one I use regularly myself, the one I actually pay for to use for myself. But ultimately, it gave sort of like all of them gave very similar answers to me. They fit the model. They gave some R code to do it with. Was it correct? I mean, yes, I personally wouldn't give this particular code like full score, only because I don't know who needs to write a bunch of like cat statements. I would do this in a Quarto document and actually write in Markdown as opposed to make R printout sentences for me. So maybe it's a yes, maybe it's a maybe. Would it get full credit? And I would say the answer is no, it wouldn't get full credit. It says that it doesn't have, one of the predictors does not have a substantial impact on the response. I've said nothing about how these data were collected. Was this an observational study or not? So verbatim copy paste of this answer would not get full credit. It also says at the bottom, there's like, I did some diagnostics, negative binomial would be a better choice. I mean, negative binomial is a more flexible model, but I know these data. I actually randomly generated the data from a Poisson model. So the negative binomial is not necessarily a better fit. The thing is, it's probably the most common thing that's being said out there, as opposed to what's happening when you actually look at these data. Now, would it get partial credit though? And the answer is, Yeah, probably. I mean, if a student wrote this answer, I would never give a 0 to that answer. There's a lot that takes from going from an empty paper to this statement here. A student who's able to create this has learned some things. Now, the probably though is if a student has just copied and pasted it, how are we rewarding effort still with partial credit? So that's something that's sort of in the back of my head is like all my teaching career, I've thought about partial credit a little bit like how can we reward effort? How can we reward maybe retaining some things from the class, even if not mastery of the full material? And now effort is greatly diminished. All of this happened by simply copying and pasting the response, and you get to something reasonable sounding really quickly. So what does that mean for partial credit? I don't know. I don't have answers necessarily, but I don't know. Now, I'm going to give you this pop quiz one more time. What would you do if this was given to you and you weren't going to just copy and paste it into ChatGPT? You have a data set with one outcome and two predictors, and someone says fit a model. What's the first thing that you would do?
Import scikit-learn.
Import scikit-learn, sure, import scikit-learn. But then what's the next thing that you would do? Personally, I would plot the data. And if I plot the data, what do we see here? What kind of a model should we be fitting? It needs an interaction effect. None of these tools fit an interaction effect. I gave this example to a colleague who just gave a take-home exam. We just finished our semester at Duke. 28 out of the 33 students in the class did not fit an interaction effect model. Like no one looked at the data and they were rolling with sort of the suggestions out there. Now, it is possible that some of these AI tools could get here, especially if it's a tool that can execute code and then also look at the plot results as well. I realize that these tools are developing in this manner, but a lot of our students are not using the agentic tools necessarily. They're doing the copy paste of the prompts into a chat interface. So not really fully leveraging the power of everything that these models can do. And so they're sort of randomly sampling from the ether what are the most common approaches here? And we're missing this. And that piece is sort of what motivates me to think there's still value in what I am trying to teach and what we're trying to teach in terms of an undergraduate statistics curriculum, even when there's tools that can generate code faster than our students can. Here's a quote from David Spiegelhalter that says, there's no substitute for simply looking at data properly. And that's sort of what I hope that we can continue to teach our students to do, because if we can do that, then sure, let them ask AI how to write the scikit-learn code to fit the model. That is of no problem to me, to be perfectly honest. Now, this is from my abstract for this talk. This talk examines how statisticians can reimagine curricula by embracing computation as a foundational element rather than an afterthought. I'm a bit of an overpromiser. I don't know if I'm really going to do that, but let's give it a try. So I want to talk a little bit about our curriculum, our undergraduate curriculum at Duke. In addition to teaching at Duke, I'm the director of undergraduate studies. And over the last 15 years of me being there, we've really tried to revamp how we approach undergraduate education. And one of the things that we've really tried to remind ourselves is that we need to think about the curriculum as a whole for the students who choose to stick with us, as opposed to thinking about each course on their own, while of course still maintaining freedom for the individual faculty who teach these courses. We're not trying to dictate every single thing, but there needs to be a thread that runs through them. Most of our students start with an introductory data science course, and they all have to end with a case studies course. In the interim, they take probability, they take regression, they take a math stat course, a statistical computing course, and a Bayesian modeling course. And these are the core courses for the major. Everyone needs to take these courses. They also take 3 electives. A lot of these courses have computational labs, some obvious that they would, and some maybe not so obvious that they would. But even our probability course comes with a computational lab attached to it. And they'll also see some computational lab components in some of the electives they take as well. So all of the classes culminate, the major culminates in an open-ended case studies course that highlights creativity and modeling. And I'm going to give a couple of examples from my colleagues' courses and then end with the intro data science course and go into more depth on that since that's the one I regularly use. So here's an example from that case studies course. This was a data set on cricket flour. You can make high protein flour from crickets to bugs. And the idea here is that we ask the students to provide a high quality, careful exploratory analysis and tell us if there's anything unusual about the data that they might see. And then we also say fit a model as well, basically, or fit some models and explain your reasoning. Now, this is a sort of prompt I couldn't get away with giving in my intro course because it's too vague. But in the case studies course, we can say, just go at it. You've learned for 4 years now. And you can see that in the case studies course, every single case study is submitted as a GitHub repository with at a minimum, a reproducible Corto document. There is zero instruction of how to do this in the case studies course anymore because we don't need to teach it. They've been doing it since day one of their curriculum to begin with. So we really can take the time in the higher level courses to go into the modeling and data exploration pieces as opposed to teach the logistics to the courses. Take one step back. In the stack computing course, we emphasize writing quality code, even in an era where you can generate code pretty cheaply nowadays. You can generate lots of code with AI. Taste is harder to teach, turns out, to AI. So here's an example of I don't know if you know this comedian, Mitch Hedberg, this late comedian, but he has this joke that says, La Quinta is Spanish for next to Denny's. If you ever travel throughout the US, if you see a La Quinta, there's usually a Denny's restaurant right nearby. So the example of, is this true? So we asked the students to scrape the Denny's website for locations, and that's a pretty sort of like tricky task in terms of how they have their website set up. And they also have to write a make file that will run the R scripts and sort of like render the report, just to give them pieces of like other tools you can use for reproducibility. They then have to scrape La Quinta website as well for their locations too. And then finally do, if you will, some stats. What's the definition of distance and how do we find distance between 2 points? And then how do we actually evaluate if this joke is true? We can't just, a vector of distances is not helpful. We need to evaluate to see, is there some support to this argument? So we need to say something statistical about that. And all of the code needs to run in a way such that when you push to your GitHub repository, the GitHub action needs to be able to rerun all of your code. Take another step back. In the probability theory course, we still continue to value explicit computing instruction in the lab component. So the lectures are where you do the traditional probability theory introduction, and the lab is, instead of writing proofs, where students are using simulations to sort of prove things along the way. But we start the simulations with something hopefully that may be fun. I myself am not a musical instrument player, sadly, but many of our students do play, and our instructor who has been recently teaching the probability theory course does as well. And the idea was to make some music with R. So there's an R package that will do this for you, that will actually generate the audio files for you. The goal is to write some transition probabilities from one note to another, and then actually sonify this in a way such that you can see as you change the probability distributions, how does the music sound? So let me show you what that might look like. For some of you, this might actually mean something, the music. For some of you, it might not. But the idea is that the students are asked to play with sort of random, generated from random distributions in R, and then try to create music that for some reason sounds good to them. And then in their answer, they need to say something about why that sounded good to them. Are they necessarily, it's the goal of teaching music? No, not at all. But the goal is to say, as you change the probabilities, the transition probabilities from one note to another, we can actually just hear the difference. And that's one way of maybe making probability tangible in addition to the mathematical effort. And it's an opportunity to keep them writing R code, even in their theory course to begin with. And majority of our students, a huge majority of our students start in the data science course. We do not require this course for the major because there are a few folks who will come in their junior year coming from probability and saying, I'm really interested in this. And we sort of like let them continue on with the regression course. But a lot of students get drawn to the statistics major because they start with this introductory data science course. And the course is designed around the Harvard Data Science textbook to begin with. That's sort of the first half of the course. And then we also have a modeling piece to the course as well. So we go through, inspired by this, the Krebs cycle, as I like to call it, of data science. This is what the course structure looks like. It's comprised of 5 units. We start with a hello world, where we introduce students to the computational toolkit. This is a week or so long. The students are writing code in R in our studio. We might revisit this repository next year, we'll see. But importantly, they're writing reproducible Porto documents, and every single thing they submit is a GitHub repository. So they are learning to use Git from day one, but really baby Git, like commit, push, that's about it to begin with. In Unit 1, we start with exploring data. The goal here is teach them the basics of tidyverse, but also hopefully instill some curiosity in them. So every single thing is presented as a data problem they may want to solve. We start by visualizing data, then we take a step back and say, what if the data isn't ready to be visualized? Maybe we need to merge 2 data sets, maybe we need to reshape our data. Then we take another step back and say, maybe we don't even have data in a tabular format yet. How do we get it into R? How do we scrape it off the web? And that's where sort of the first unit ends. And soon as we've talked about web scraping, becomes a great opportunity to pause on writing code for a little bit and talk a bit about ethics. So this becomes a nice foray into talking about data privacy. Should we scrape even when we can scrape? And what do we do with the data that we have scraped and who does it belong to? And gives us an opportunity to talk about ethics for a week while the students are developing their project pitches for the end of semester projects. And then we dive into the making rigorous conclusions unit, which is the more statistical unit, if you will. We start by building models, building predictive models, and also doing a bit of inference. And the inference is primarily focusing on building confidence intervals using bootstrapping. So we keep the computational element even as we dive into the slightly more traditional statistical inference topics. And here we're introducing tidy models as a toolkit and bringing in complexity. And the last unit is my favorite unit, the looking further unit. This is the unit where, as an instructor, you say the world is my oyster this time, or maybe you ask the students, what do you want to learn? The best way to learn something as an educator is to put it on your syllabus. And when that week comes, you have to learn it. There's just no other way. So by public commitment and fear of public shaming, I have learned a lot of things over the years. And importantly, throughout this entire sort of segment, there's communicate. Every single piece of code that's written that generates a plot or a number or any sort of output has to be interpreted as well. And the communication piece is key so that the students aren't just generating answers, but also stopping and answering data questions along with the with whatever they're getting to with their computational skills as well. So I'll give you a few examples from the course. The first one is a very, very sort of generic common example of joining 2 data sets. Probably any data science course, any data science book at some point touches on that. We have a data set of countries and we have a data set of continents, and we need to join these together is the goal. We can join them easy enough, right? That's the easy piece of this. Then we ask the students to pause, even when your code does run without error. Did it actually do what it wanted you to do? And as the data size grows, about 200 countries is a good size for you really can make yourself scroll through the output, but probably you wouldn't unless someone told you to do so. And we ask the students to look and they see that some of the countries have not been joined and we don't have a continent attached to them. Now take a look at the names of these countries. Why have they not been joined? Well, are probably spelling issues. And then we get into the issue of what's a country? How many countries are there in the world? So we get to talk not just about data cleaning. Yeah, we can input the NAs with a case when statement, but what's the definition of a country? Who decides that? Where do your data sources come from? And as a data scientist, when you write a case when statement like this, saying that I am going to assign a particular country to a particular continent, is this something you need to disclose or not? So this becomes an opportunity to sort of like foreshadow into talking about ethics as well. And then we do some things you can expect, like we can make a bad plot, then we can make it a better plot. It's a great opportunity to introduce a tiny bit of mapping and choropleth maps. They're not great, but that's a good skill to have. And it's really sort of satisfying in week 4 of the first programming course you might be taking that you get to make some pretty maps, even if there may not be the best way to, represent all types of data. And the idea of iteration comes into play where the first plot you make is probably not the best one, even if it runs without errors. Another example I want to give from the course is based on web scraping, let's say, and you'll see me, many other educators saying, I like using data sets students are interested in. Well, turns out as I age, I have much less idea what my students are interested in. And I have a child who's now much younger than my students, so that's of no help either. So they're in this lost zone. So if any 40-something-year-old tells you we're using data sets my students are interested in, they're lying to you. We have no freaking clue what they're interested in. But one thing that has not swayed me the wrong way is people are interested in hearing about themselves, turns out. So the Chronicle is the student-run newspaper. And we scrape data from that. One of these days I'll get banned, but it hasn't happened yet. We scrape the opinion pieces on the Chronicle, and it turns out our students have very specific opinions on people who write opinion pieces. So they actually perk up and start listening. And so first becomes a web scraping lecture of like, how do we take semi-structured data? It looks structured here, every entry, but you can imagine some of them are missing dates, some of them are missing authors, whatever, all the complexities of web scraping comes in. And then we create a data frame in R. And then we also stop and say, now we can scrape these data, but how do we learn about whether we are, one, allowed to scrape the data? So we talk about websites having a robots.txt file and how you can inspect that programmatically. And also, should we be scraping these data? Is this ethically okay or not? Then we do some text analysis. Students talk about Duke a lot. Okay, nothing that interesting here, but it becomes an opportunity to say, now we have data that is text strings, and tokenization is one common way of starting working with some data. So we at least get to introduce this as an idea to the students and then make a boring bar plot. But once we have done this and we have this idea of we can break apart the text, then becomes an opportunity to do some sentiment analysis. So here we have taken the top 10 positive and top 10 negative sentiment authors based on the pieces that they have contributed. Now, these names mean nothing to you, I bet. When I ran this last year, I think this was the data from May 12th last year. I was just wrapping up teaching this course. 2 of those students happen to be in the room with us. Many of the students are students that people know. And guess what? I won't name names, but one of the negative Nellies is actually the only faculty member who contributes to opinion pieces on the student newspaper, and students get a kick out of seeing that name there as well. Now, sentiment analysis by joining a tokenized set of words with a bag of words has its limitations, of course, but it's a good start to thinking about how we take text and then turn it into something else that's analyzable. And turns out when you put your students' names or their friends' names on the screen, and hopefully a way that is not in any way like calling out anything related to their course performance, it becomes a way of figuring out what might interest your students and, get them to actually keep looking and learning. The last example I will give from the course is a very, I would say, traditional example. Any stats textbook that is, written after email or at least after spam email probably has an example about predicting whether an email is spam or not. So here is a really bad starting model of predicting whether an email is spam or not based on the number of characters in the email text. This becomes an opportunity to just introduce logistic regression and classification. But then we get to talk a little bit about decision errors and the idea of sensitivity and specificity. And it is my belief that one of the most important things we as statisticians can teach anyone, whether that person will take one statistics course or many, is idea of sensitivity and specificity and false positive and false negative errors. Because no matter who you are, chances are at some point a doctor will quote a probability to you, and chances are they will misquote that probability to you more likely than not. Or even if they are not making a mistake about the probability, they may not be well equipped at a time of distress for you to really communicate to you how you take that number and make a health decision about yourself or a loved one. So it becomes a good opportunity to just pause and talk about these things. And then we bring in a little bit more here. We don't actually teach loss functions in this course, but my goal at the end of this course is for many of the students whose interests have been piqued to go ahead and take the next course, the regression course, where they will get further into this. And for those students to talk about, here's a very sort of like standard decision table you might see. But what if we change the labels and now we're talking about whether a patient has cancer or not? Or whether we're talking about whether a defendant will reoffend or not. And based on that, we're going to make some decisions about whether they go out on parole. When the loss functions change, how do we actually value the probabilities associated with a false positive and false negative? We don't go then further into enumerating what's L1, L2, or whatnot, but we at least tell them that now you know how to calculate the probabilities, but there's more to explore here. Go take the regression course to do so. Now, I could, keep going with examples from this course. If it's not clear here, I enjoy teaching this course. I enjoy swapping out the examples every single semester. It's what keeps it fresh for me, hopefully, and for my students. And it's been a great pipeline into our major. My goal isn't 300 students take this class every semester. Not all of them become stats majors, and that's not the goal either. But for those whose interest is piqued, they have a really good foundation for being able to run through the rest of the curriculum and the major. What I'll do for a little bit, change gears, is talk a little bit about pedagogy and assessment and challenges, and particularly in light of AI, which has been, in a way keeping me up at night and in a way giving me new projects to work on as an educator. Here was the AI policy that I had in my course the last time I taught it. Turns out it was like a little too optimistic, even though I felt good about having something on my syllabus. Basically said, you can use it to generate code, but you must cite it. You can't use it to write narrative. Honestly, I just don't want to read narrative written by a robot. And more importantly, neither do my TAs, who are students themselves. And for learning, yeah, sure. I mean, if it's available to you, just use it. But, bear in mind that it may steer you in directions that are going far away from what this course is focusing. A lot of times I hear like AI may be wrong. Sure. But like every single day, it's less and less likely that an AI tool's answer will be wrong about something we cover in an introductory data science course. It is still quite likely that it will steer people in the wrong direction in terms of a path to success in the course, because it is not aware of sort of like what's really the focuses in the course. So what we are doing in an effort to sort of like synthesize all of this and update our policies and assessment procedures, I'll try to summarize it in 3 steps. One is moving more assignments and assessments to the classroom. 2 is leveling the playing field with explicit how to best AI instruction. And then 3, I'll spend a bit more time on this, shifting AI use away from taking shortcuts towards supporting learning. So number 1 is probably something you've heard of regularly. Oh, we do more in-class exams because of AI. Okay, now we're back to like my college years, perhaps, but maybe with good reason. So let's take a look at assessed work and where it's being done, at least in this course. In 2024, this is what the assessment structure in this class looked like. We had a midterm exam, and part of it was in class and part of it was take home. And then we had a final exam that was all in class. And everything else, you can see a huge portion was happening basically at home. The homework assignments or the labs that basically where you start in the lab and then go and finish it at home as a homework assignment was really where we were thinking this is where learning is happening and that's where points for the course should come from. Over the years, what we've realized is that not as much learning is happening going through those, because when students are stuck, they're not necessarily coming to office hours to do a deeper dive and learn with us. Instead, majority of them are taking these shortcuts. And on one hand, that frustrates me. On the other hand, if you have N hours and you want an optimal path to points, not learning, to points, that may not be a bad approach, so it depends on what you're optimizing on. So in 2025, what we've done instead is break things up a little bit. More in-class exam time. I haven't given up on the take-home portion of the exams yet. I think they are valuable, but I'll say a bit more about that. We still have the final, but as you can see, we have divided what happens in those labs into lab and homework and tried to bring more of like in-class work on problems in a structured manner so that we can show the value of working with people in the class to students. So I'll give you an example from one of these restructured labs where the restructure was motivated by sort of like students taking shortcuts through AI, but I think it has had better, like more important effects than just that. And this was reflected in the course evaluations as an enjoyable part of class where learning is happening as well. So in the labs now, students work with mostly toy data versus in the homework assignments, they're working with real data where like they actually are solving a real problem. So we have a toy data set, the goal being that it can fit on a screen is what it is. So people can tangibly do things with their hands before writing code. So we have half the data. This is our X variable, and you are asked to make Y not simulate, but like literally like make it up, the Y variable, so that you end up with the following statements being true. For each additional unit in X, Y is expected to be lower on average by 2 units. So that's about the slope, something about the intercept, something about the R squared or the correlation coefficient. And we put the students in teams and they just need to sort of make up data. We also tell them don't use AI for this. And like there's TAs running around and they're not doing that right at that time. So there's one of them making up some numbers, one of them plotting it, looking at it and whatnot. And they're playing around to sort of find the answers. And then once they do, they need to answer a bunch of questions based on that data. This has been a great way of like getting them to see how as one of the variables changes, that will impact the slope or the intercept. And the idea of working with a small data set here is that it's something reasonable for us to say in a class period, you're actually going to be able to solve this. And by being there that day and participating in this, you get the points for that day, basically. Here's another example where we say you're going to explore the relationship between distance and air time of flights. But we like grab a new data set of our local airport. And we ask them to take a random sample, visualize the relationship between these two, fit a model, and then come to the front of the classroom and on a number line, actually put the slope that they have calculated from their random sample. And if you have about 10 teams in your class, then you start to see basically a sampling distribution or bootstrap distribution being built. So they know how to write the code to generate these things, like generate from the entire population themselves. But instead of having them do that, we make them take a single sample and then build the sampling distribution just individually by like manually on the board. And so you can't actually get through this exercise if you're doing it at home. You need to be in the classroom to be doing it. And then the TAs get a chance to sort of actually explain these ideas, which happen to be one of the harder things to be teaching in an intro stat course to the students. This also has worked out nicely, and I will say from our TAs who are PhD students, master's students, and undergraduate students, a positive piece of feedback that I have heard is that they've always enjoyed helping students in lab, but the opportunity to do some mini lectures has also been rewarding. And, it's given them a little bit more of a sense of purpose and a sort of present themselves as a person of authority on the material in the classroom, which they have liked. So that's been a nice side benefit of this as well. In addition to the homework piece, some of it coming into the class with the exams, we've had for years and years, I've had the structure, you come and take an in-class exam, and then you do the take home. What I'm planning to work with, so ask me after next fall how this works, is give the take-home exam to them prior to it, a few days prior, not the night before, but prior to it. And then in the class exam, we give them an excerpt from the key, not necessarily their own answer, but from the key, and explain what's happening here. Why did we make these choices in the code? So they're not generating code themselves on a written exam where they can't like Google things, but they are given a model answer. And if they actually had worked on the take-home exam themselves, that plus everything that happened in the course, explain what this code is doing should be an exercise that is maybe not trivial, but definitely doable for them. And what I am feeling as I use more AI tools for generating code, and what I hear from other colleagues who do this regularly, is that many more people are spending a lot more time reading code than writing. This is an opportunity to hopefully drive students to read the code as well. So even if they are using these outside tools in the take-home exam, hopefully they're pausing and reading it before turning it in. Leveling the playing field with explicit how to best AI instruction. I've done things like this in the past where I'm like, I have a lecture dedicated to, I say ChatGPT here because that's what Duke gives free access to students. So I talk about that, fully acknowledging that all my students tell me we don't use that one. We think our teachers are going to look into it. So we use our own thing, but whatever. But that's the one I sort of like talk about in class. And I give them some instruction. Though what the students have told me is that they don't like lectures like that, but they love tips like that. So more and more, I've broken it down throughout the semester, as opposed to making it like a single day on like, we're going to teach you how to use AI. Just give the tips along the way. Additionally, we ask them to cite things. Well, citing things is hard in general, but giving explicit instruction on how to cite, which by the way, changes every day because these tools change how you can generate a sharing link from their threads just like about every day. But keeping those instructions updated can be helpful for the students. And then finally, this is the lesson you're going to have to change all the time, basically, because nothing is stable here. And lastly, I want to talk a little bit about how I've taken this as like a motivation for myself to learn some new things and build some tooling. So the problem statement, if you will, is that increasing number of students use AI tools as a first step before even thinking about it. What I mean here in fancy words is they're just like copying and pasting the homework assignment and then copying and pasting the results from something like ChatGPT. Let's call this motivation instead of problem, and let's try to find a solution, or maybe a potential solution, if you will. Can we use AI to give them just-in-time feedback that is structured just like feedback on graded work? And can that maybe stop them from, feeding AI answers into an AI tool in the first place? So here's an example of what this looks like. This is an evolving tool, and I'm working on sort of like some both user interface updates to it and also the underlying model. But here's an example of a homework assignment that a student may have worked on. And what they're doing is they're asking to get feedback, and they can do this right in the IDE. And while this is sort of like turning, it is actually querying sending a API call to an LLM that also has my rubric. So these bolded items are the rubrics that we use for grading with our TAs. And then it's evaluating it against that and giving the student feedback just in time. Here's another example of this where the student gets more of them wrong, and then it gives them more feedback with that. The goal here is that we know they're using these tools anyway, but they're not necessarily always getting the best advice from the tools because the tools don't have access to how I evaluate their work. So this is bringing how we evaluate their work to them. And what we're going to be doing starting next fall is we give them the AI feedback for all of the questions. Instead of hiding it away from them, we give them the feedback for all of the questions. And then we grade like a randomly selected number of questions from within them. So the students have the opportunity to ace these homework assignments, which they always did anyway, but at least this way they're hopefully doing it in a better, like more structured way and getting it not by just adding up those partial credits that we were giving them, but actually because they are able to arrive at the right answers because their answers are getting evaluated against the rubric. It's been a fun project to work on. It's allowed me to learn about how models work and also program around them as well. So I would say that as an educator, I like taking these like problems and checking to see like, could I use it to learn something myself? And I would say the project has been helpful for that. Is this a big like learning gain for the students? That is not a claim I am making in any way. I don't think it's a loss. It's something we'll evaluate along the way. But thank you so much for listening.